Hello. Thank you, everyone. We are back with Space Day here at Concordia University's For Space. Thank you for joining us. So right now, we're going to get started with our next workshop, which is the Intro to Embedded Programming workshop. And we are doing so today just to help situate you. We are streaming to YouTube Live from ForSpace, which is located on unceded Indigenous lands in Tiohtià:ke, Montreal. At ForSpace, we work with our university community to mobilize knowledge by co-creating daily activities, to examine research questions and projects that are in development here at the university. So today, we are running a series of workshops and conversations as live stream meetings. And so we welcome your comments and questions with a raised hand or via the chat if you're joining by Zoom. For those of you in the space, if you'd like to participate, you can let us know by raising a hand, and they will be calling people up at the end of the presentation to try out firsthand. So with that, it is now my pleasure to pass the microphone on over to CDH lead Amro and CHD member Rowan from the Spacecraft Division. Take it away.
Thank you so much. Okay. Welcome, everybody. Welcome, everybody, to the Intro to Embedded Programming workshop. We're just going to give you guys a little quick, very basic and simple tour into what we do as a software team in the Space Concordia ecosystem. This is essentially what every software subsystem does in all the divisions. Yeah, let's just get straight into it.
So, embedded programming can seem quite daunting, even if you have a background in regular programming. So to give like a quick definition of it, embedded programming is basically writing code for embedded systems. Embedded systems being very simplified computers that we call microcontrollers. We have a few of them on the desk over here that we're going to show you kind of like how to hook up and run code on in a bit. So this is with the purpose of accomplishing a very specific task. So you might have a microcontroller that controls the direction or the movement of something, and so you write code very specifically to accomplish that task. So without embedded programming, each component would basically be a chunk of metal. It wouldn't do any of its tasks properly, and so it's very important that you have everything hooked up, connected together. The core aspect that you have to remember is that there is no UI, there's no programming interface that will give you feedback when you're embedded programming. So you have to really make sure that your code does exactly what it's supposed to do and not just what you assume it should be doing. This can make it definitely, this is what makes it the most daunting. But you figure out a lot of different ways to do debugging and stuff that are quite different from when you do classic programming.
Yeah, so basically we like to look over at the different stages. We call them layers in programming as a pyramid. So the very, very lowest layer, which is basically how your computer talks to one another, is simply ones and zeros. That's kind of below assembly code. It's called machine language, and it's just a lot of binary, ones and zeros. But really, a programmer's job starts at assembly code. So assembly code, which we'll show you soon, is the nearest representation of machine language. Above that is embedded programming, which is what we do. Now, embedded programming is a little bit fancier programming, a little bit more readable for the eye. And that's what we work on. And it kind of has the perfect balance between human readability and also closeness to machine language. You'll see that the layer above that are high-level languages, which are like languages, if you've ever coded before, like Python, like Java. These kind of languages are quite far from machine language. And it doesn't actually require you to do any what we call low-level engineering, like understanding how the CPU works and whatnot. It simply does all the work for you. But embedded programming is kind of that sweet spot that is necessary for us to work on boards like these. Above high-level languages are basically operating softwares that are already doing all the work for you. Like imagine think of your phone. You turn an option on and off. Let's say your brightness dial. You raise it up, you raise it down. Your phone does that already for you. Now you'd understand at a lower level, which that is the case for every sort of device. It starts off at some low level, but it's just built up. There are sort of values for that. It's a value that is constantly going up and down for whenever you're changing your brightness. How we work in embedded programming is with microcontrollers like these, as Rowan said. These are the microcontrollers that we kind of upload code on, and they sort of house the code that we work on. We're gonna show you guys an example of how two boards communicate later on, but that's essentially what you're seeing over there. So, what are registers? Registers are simply, so remember when I said about the brightness? So in the lowest level, simply every hardware that has a brain is what we call a processor. Every processor has registers. All these registers are for is to simply hold data and store data. And what data they're storing? They're storing simply numbers. So you'd realize that in the lowest level, your registers, what your computer is doing is just a lot of math. And that's why people tell you that computer engineering and software engineering is just a lot of math, is because in the lowest level, all that is doing is math. For example, think of the CPU as just a calculator with a bunch of free space to store numbers. That free space is what we call registers. And to perform any task or any operation, it all depends on manipulating those values in the registers. So your entire computer is based on math. For example, let's just use the simple example of a calculator on your machine. Doing calculations on a calculator on your phone simply allocates numbers that you put into a register, and then the operation that you put into another register, and then the next number that you put in another register. And with whatever you put in, it will do the, for example, let's say you're adding two numbers, it will add both registers and store them in another register. So that register, which is just free space, will now be allocated with that data, and that data will be shown back to you.
So when doing embedded programming, knowing about these registers is necessary because you will often have to directly interact with them. When you're coding in Python or Java, you won't necessarily think about where your data is being stored and like what your code is doing to the physical machine. But when you do embedded programming, you might have to directly put numbers in a register that will affect some value. And to know what that value will be doing in that register, we have gigantic documents called data sheets, which are specific to each different kind of board. So when you do embedded programming, you do a lot of looking up what exactly you're trying to do, what physical space in your chip you're aiming for, and then you're going to go back to the code and put those values directly in. So just as a fun fact, there's thousands of these registers on a regular computer, so on every computer on this desk, and the data is being manipulated and moved around in those registers at lightning speed.
So this is an example of assembly code. Now, here's the thing. One question that's quite asked is why do we need assembly code? Why can't just we use this readable code and code the microcontrollers? So that's the thing. These microcontrollers, you have to remember that they're just chunks of metal. How they communicate is through machine language. The closest representation to machine language is, as I said, was assembly code. And this is what assembly code looks like. On the right side, that's assembly code. If my job was to code like that all day, no. Simply because it is entirely unreadable, and so it's quite hard to code like that. Now there are programming languages that their job is to simply convert your code to assembly code. So why do we do that? Is because they're much easier to read, and so it is much easier on the programmer to do. On the left side, that's C code. You may have heard of it before. So as you can see, it's much readable. On the right side, you wouldn't have even known the kind of function that is happening in function foo. But on the left side, the C code, you can see that it's simply checking if one number is greater than the other. If it is, return this number. If it's not, return the other number. done. Um, so, as I said, you might be familiar with Java and Python. They're very high-level languages. C is a bit lower level, as I said, because we are much closer to directly manipulating assembly code. And it's also much faster, and that is necessary when you're coding, boards that barely have storage. They have low RAM speeds, computing speeds, and exactly, yeah.
We actually use C when we do embedded coding in Space Concordia. So our main language is C, and we work with C with minimal libraries, and the libraries that we use are very specific to flight softwares. So it's much more readable than assembly, but still you gotta refer back to your data sheets all the time. So embedded programming really has us interacting closely with the hardware because it allows us to manipulate real life hardware and control them. So if we were to hook up something like a servo, which we'll be actually talking about during our workshop, you would need the code to physically move these pieces around. And that's something that you might not be able to see the leap from coding in Java to to physical movement, and embedded kind of allows that. So unlike much higher level programming, it's very power efficient, as he said before, and it's lightweight, and this is why it's preferred for flight software, because you can't have, when you send something to space, you can't have it be taking up a lot of power, or else your satellite is just going to go into sleep mode all the time.
Yeah, so as Rowan said, people and programmers use embedded to bridge the gap between software and hardware. And although it may be daunting in the beginning, I understand, but it is simply just a slow process that you have to ease into. Usually people understand that software stays software, and hardware stays hardware. That's not the case. Many of the things that you use, they're just chunks of metal, and they wouldn't be operational without some code. So the software is necessary to make hardware work. As you can see right there, simply just some code can make us like move. This is what's called a servo. Move servos around, and they're physically. And for example, these LEDs, it's only just digital code that's allowing them to turn on and turn off. So the coolest thing about embedded programming, what you can do is to see your code come to life. And that is really the funnest part about embedded programming. The most unfun part is coming soon. We'll talk about it. And you may have heard of Arduino before, which is a commonly used interface to introduce people to embedded. The activity that we will do will let us use an online simulator of Arduino, which will help us illustrate what actually happens in real life. So you'll get a good simulated taste, I guess you could say.
Okay, so we mentioned before that it can be daunting and there's kind of a steep learning curve for embedded. And the reason is debugging the code, seeing why something doesn't work when you plug your board in and when you flash your code to it. For anybody here who does code, software bugs, very common, and you can solve them by using the built-in debugger or by printing. That's the kind of default one a lot of people use. But for embedded, there's no screen to give you feedback a lot of the time. You have LEDs, which might serve a purpose. If you want to make sure that your code is getting to a certain block, you can turn an LED on or something. But it's definitely much more labor intensive to debug embedded code than it is to simply debug code that you're writing in an IDE. So the different methods to use to debug could be using an oscillator, which you see on the left, which shows you the actual signals coming between the two boards. And from there you can pinpoint, oh, maybe the signal is too low here and I know that it's supposed to be high. On the right side, you can see the logic analyzer, which is kind of like a sophisticated oscillator where you can take snapshots of the signal coming between the two boards and kind of pinpoint where it should be. The reason that the signals are so important is because the boards communicate using different protocols that rely on these signals. So as an embedded engineer, you really have to have an eye for the unexpected. So your code might seem like it's behaving, but it's doing something else in the background that would be totally detrimental to your mission. So you have to be able to spot things that might be a little out of the ordinary and be able to check that your code is 100% doing exactly what you want it to be doing.
Yeah, which is sometimes tricky because there is a lot of false positives. You may be getting something to work, but not realizing that it's messing something else underneath. You need to make sure that what your code is doing is quite independent. Whatever is working should only make that work and not making something else not work. So when you have several things that you're doing, it gets quite a bit tricky. Just to make sure that it pans out everything, and nothing is confusing with something else. And it's quite common to see unexpected behavior. To code something and expect it to do something, but then you get no response. And that's exactly when we debug. For example, we use the oscillator to check, maybe my serial communication device wasn't even sending a signal. That's why I'm not receiving any input. Stuff like that. So as an embedded engineer, the issues can either be software or hardware. And that's the hardest part, is because as just a programmer, you know that your stuff is only software related, and you don't really need to worry about your machine making a mistake or whatever. But no, here in embedded programming, it's your machine can make a mistake and your software can make a mistake, and that's what makes it a little bit more difficult.
One of the simplest things that we have debugged before in our space lab is using a voltmeter. We realized that some of the pins had been connected wrong, so the power wasn't going where it was supposed to. And after an hour of trying to debug the software, you figure out, actually it's like a very simple mistake.
Yeah.
So
some pins weren't connected in the proper slots, and we're like, we thought that they were connected the whole time. So the emphasis on having an eye out for these things is quite critical. Why is it necessary for Space Concordia? So now we bridge the gap between what this kind of work is and what our mission is. So SC Friar, our newest satellite, is set to launch in 2026. And we will study the growth of yeast strains in space, basically trying to see how space affects yeast growth, and also detect forest fires using AI by a camera on board. You need to make sure that the satellite is autonomous, because it's not always going to have connection to Earth. It's going to be spinning around the globe. Which is why we have to make sure that the system on board never malfunctions, because understand that a malfunction here on your code, in your Python code, on your website, I messed up, let me just rewrite it. That's impossible in space. One malfunction and you can never fix anything ever again. You can't just simply refresh. You can't simply reboot. You need to make sure that and that's the hardest part in our job, is because we kind of try our best we can to simulate the environment on Earth to make sure that nothing fails in space. And we have failing mechanisms. If something ever fails, if power shuts down, what happens? We have bootloader systems and stuff like that. So it's really necessary for Space Concordia, for anybody to come here, for us, for you to come here, and make sure that you write code that's readable for other users to read, and also code that is fail-safe. And you could say that the mission is entirely dependent on many different factors, but it's hugely dependent on the software team to make sure that it doesn't just remain a hunk of metal in space. Because if the software doesn't work, then it's just yet another rock in space.
this might seem like it's going to scare you off or something, but we have a very welcoming atmosphere in our lab. Everybody helps each other out. If you make mistakes now, it's fine. There's other people that are looking at your code with you. It's always great to pair program and stuff like that. So don't let that scare you off.
Yeah.
And actually, if you're interested in joining, the workshop we'll be doing today is actually the intro task for the CDH subdivision. So when you want to join Space Concordia, you complete a task and you mail it to one of the members who can look it over and then talk with you and then onboard you into the team. And so the one we'll be doing today is exactly that. It's the task that you can do. So you can learn about how to do it here, you can complete it here and save it, and then use that with your application. We'll be following along on Walkwe.
.com.
Yeah.
If you have a laptop with you, then good. If not, even better. We have laptops right here ready to be used. Before we do the intro task, we will just show a little demonstration of the real life aspect of how embedded programming works. So, as you can see right here, we have,
We're gonna have to move this.
yeah, just close that. We have two boards right here, and we're gonna try to make them communicate. As you can see, it's a lot of wiring, and it is, and there's a breadboard just to connect the wires together. Now, it may seem daunting. We said this several times, but simply how I see it is when you put yourself in a steep enough learning curve, you will learn quite fast. And that's the case with me. I joined Space Concordia about a year ago, and I understood nothing. But it's just being around people that know what they're doing makes you learn quite fast. If you've ever heard of the saying of, if you want to be faster, just run with people that are way faster than you. So that's the case, and you learn quite fast, and it gets you up to pace. And the best thing about that is when you're constantly around people that are like way better than you, is that you can then be better than your peers that are at your level. So it's just a simple case of hard work and how much you want to better yourself. So what we have right here is called a Teensy, and this is an Arduino chip. And this is what will allow us to use simply like a simple interface to code on. That is quite easy. And why we code on this and not like more sophisticated boards is because, or more sophisticated chips, is because we know this works. We know the Arduino IDE works. So when you're testing stuff out, you want to minimize the number of factors or sources of error, and you want to make sure, and then slowly you can branch out to, other boards that you don't know will work or not.
Hey everyone, Birdie here from ForSpace. I'm just interrupting really quick, just letting you guys know, I know that it's really noisy in here, and for those of you online, we just have our front doors open, so we're getting a lot of noise from across the street. It's back to school, frosh, all that exciting stuff. So I just wanted to say for those of you online, we're sorry if there's some interfering noise, and if you have any questions, you can pop those in the chat, and I know that our facilitators will be happy to answer any questions in case there's anything you can't hear. All right, that's all for me. Keep going.
Okay, so there's a lot of electricity involved with embedded programming. So you deal with software, hardware, and you also deal with connecting wires. So step one, most important thing with embedded programming, never connect your wires to the boards while they're plugged into the computer or while they're plugged into a power source, like a power supply. Make sure you set up the wires correctly before you ever plug in power, because you may risk of frying the board when some things aren't connected before the others, okay? So, it gets a little tedious, but I'll try to explain it as best I can. This board, we will connect the USB to it. This USB, and it will simply be powered up. So there's a VCC pin, and VCC is simply a power pin. So what I'll try to do is I will connect this power pin to the breadboard, so I can power up the entire breadboard. And this is what we call a breadboard for anyone that doesn't know. It's simply just there's metal under all these pins, and they just make sure the pins are connected to each other. Anyway. One thing that's very important to know is that with every electronic device, you must not only power it, you must ground it. there must be a way for the power to, yes, enter, but also to leave out, to exit out. In this case, there's also called a ground pin, and it's written by GND. When I spot it over here, I'll just connect it on this breadboard so that now there's a shared ground line, right? I don't know if it's obvious, but there's two lines right here. How we usually do it is one line becomes the power line, and one line becomes the ground line, because sometimes you have to ground several components at once, and they must be all sharing the same ground for it to work, or else it wouldn't work. Now, for communication between two boards, which is what we're trying to do, we have different communication protocols. There's major ones. There's like I2C. There's SPI. There's UART. We will be using I2C here, which entirely simplifies the process because we're only simply using two wires. One is the clock line, which is called the SCL, and one is the SDA line, which is the data line. So you can understand that there's a clock line. That clock line is simply just the timer for the boards to be synchronized, you could say. And the SDA line is for the data line, is to actually send whatever data you want to send, like bytes, like messages. And that's how we will do it here.
The protocol basically allows the boards to agree what speed they're going to be talking at and how they're going to be receiving data. So they're going to receive like a byte that'll tell them like, oh, the message is starting, and then they'll receive something at the end that says the message is over. And that is how they know that they're receiving all the data they need to at the right timing and not just random data.
Yes, and right here, as I said, every component must be grounded. So I'm now grounding this TNC. As you can see, it may be a little more obvious on camera, but there's like ground wires, maybe not. There are, it shows you what pin it is. It says GND 0, 1, 2, 3, and every pin has a different use, but the ground pin is, this is what I'm using it for, is to ground it. And it happens a lot, like one of your sources of error is that you just connected to the wrong pin. You thought that this was a ground pin, but it's just a 1.7 pin, for example. Now, I've successfully grounded and, actually I forgot to power. Okay. So it will get powered from the USB, so there's no need. It will be connected like this, and we'll have another USB connected to this board. Anyway, now I will connect the I2C lines. I2C, as I said, uses two lines, one for clock, one for data. And you'll just have to know to read here. Like, for example, this says, one of these, what's written right here is 16. And, sorry, 18. And you just have to know from using the board so much that 18 is for the SDA line and 19 for the SCL line. It's by an electrical team, it's programmed directly for it to be like that. So you can't really change that on your own. You have to kind of abide by what the electrical team has done for you. So there's something called pulling up, and for I2C, you have to pull up. You have to use pull-up resistors to pull up the SCL and SDA line. It's a little bit more technical. It requires electrical engineering, prerequisite knowledge, but simply it's just to make sure that the right amount of voltage is going through it. So I will just skip through that part, and I'll just do it here really quickly.
Each of these boards come with their own data sheet, which will tell you what each pin is, how you should be connecting it. The reason that we know how to connect it is because we've been doing this every week on the space work days.
And you can too.
Yeah, practice makes perfect.
Yep. So the main important part is for a pull-up resistor to work, you connect the power to the resistor, and from the other end of the resistor, you then take your I2C lines and connect them to your boards. So, right here. And on this board, I'll just arbitrarily set this one. So there's two right here. I'll set this one to be the SDA, and the SDA on this MSP, we call it the MSP board, is 1.6. So I'll go look for the 1.6 pin and connect to it.
The MSP board is actually the kind of model of the board we'll be using in our satellite for multiple components. So that's why we brought this one today, to show you how we work with it in the lab.
Yes.
The actual board that will be going up in the satellite is made by our electrical team, though. So it's similar technology to this board.
Yep. And as I've connected the SDA line on the MSP, I have to also connect it the same exact line on this Arduino board right here. And that is important because, as we said, it's communication between the different boards. So they must be on the same line because that is how they will communicate. And same thing with the clock. So I will connect the clock line to both boards, and that will make sure that they're on the same clock, which is important for them to be synchronized with their messages. And that's simply how the I2C protocol works. So I know that the SCL line is pin 19 on the Arduino, and the SCL line on the MSP, which is the red board, is on pin
1.7.
1.7. And there you go. Now we're ready to upload code on our boards, as we've connected them successfully, hopefully. This is embedded programming where you make more mistakes than you have success. So simply we wrote code. Well, actually, before we upload,
Right.
now that we finally connected the boards correctly, now we can input the power, and now we're sure that it shouldn't fry. But if you did try to connect all the pins together while the boards weren't correctly pinned together, you would risk frying the boards, and you could tell by how hot it is, or if you can smell smoke, which has happened to me before. So.
In the lab, we work with electrostatic bracelets, which you attach to the mats that we work on and then to your wrist, and that allows any static to discharge safely and not right into the boards.
Yeah, so in I2C protocol, we kind of have a master board and a slave board, because we've set this to be the slave board. Slave board simply takes the data and handles it. It handles the data that you get sent to it from the master board. And this is what we'll use as the master board. So this will send data, this will receive the data, and then act upon that data. Yeah. So we have code here that will just send data from this Arduino chip to here, and it will make an LED here turn on and off every second. And how we've done that is we found the LED pin that's on here, and we've just set it to turn on. The code is quite technical, so I don't think we'll show it, but
it's about 150 lines or so to
yes.
get an LED to blink. So it definitely seems daunting from the outside.
Yeah, and basically we've just done it so that if it receives a certain byte from the master, it will turn on. If it receives another certain byte from the master, it will turn off. And we'll just have it on a loop. So hopefully it works.
It is uploaded.
What is?
Both of them.
You sure?
I don't know if this one had an error.
Okay. Oh, see? Embedded programming. I misconnected one of the pins. That was on purpose, guys. That was to teach you that you mess up, okay? And you mess up a lot. As I said, you barely have any feedback. Feedback is so minute that you just have to have an eye out. So when something doesn't work, you gotta look, you gotta see if every pin is connected correctly. And there you go. As you can see right here, you see this pin. Where is it? There you go. It turns on and off. And so we successfully just have now done, we have successfully made the two boards communicate only by some code, and we made something physical happen. So that is the joy of embedded programming when something like this finally works.
What's also interesting is that they're both using different languages, right? So this one, we wrote some very simple code using the Arduino IDE to send the signal, and this one we have our embedded C code that receives and processes the signal. So even though they're both using very different techniques and different hardware, you can get them to communicate.
Okay, and thank God that worked well. Now next up is we will actually show you how we, on an online simulator, just to give you a taste of how this works, we're gonna make you use an online simulator that simulates some physical parts, like a servo, like a potentiometer, and on this online simulator, we will write code to make those physical, virtual physical parts actually do some job. And if you have a laptop, of course, do it on your laptop. If not, any volunteers to come over here, and we'll walk you step by step.
And remember, this is our intro task to join CDH. So if you're interested, now's the time to learn it, like while we're here. Yeah, no.
Come on, yeah, come up. Just, we need 4 people. 4 people to take a seat, come on. Anybody, come on.
You can just go to the website we put up here, Walkwe, and
Yes.
we'll walk you through setting up the project.
Come on. We need one more. One more. Yeah, sure, come on. So, it's not only the people that are sitting down here actually working with this. We will demonstrate it on the screen as well. So, yeah, they're already on the Arduino Uno. So we will start a fresh start, and we'll go to Arduino Uno. So all of you should already be there. If you want to join with us, actually, you should probably show them how to do that again from the beginning, just from the beginning of the website.
Yep.
For anybody that wants to join. So you enter the website, you scroll down, you press on Arduino, and then you scroll down until it sees start from scratch, Arduino Uno. Okay, so you can't do embedded programming if you do not have the hardware already. So we will add some specific hardware that we will want to use. So here's the task. We want to use a potentiometer, which is simply the slide potentiometer, which is just a slider that we can slide up and down, or left or right, whatever. And we want it to rotate a certain servo. So if you remember, I showed you the servo in the presentation, and that's what it looks like. You could zoom out, like on this.
Tried, but I'm not sure how.
Does it?
On Walkwe, yeah.
No? Really?
Can I like... Strange.
That's annoying. Ah, yes, zoom out.
Of course.
There we go. And then we want also, just for fun, something that keeps the time. So we will add something called RTC, which is a very well-known like device that just, it's good to track time and take current time, for example.
So it's actually this RTC specifically?
Yeah. It's like a simple one to use.
Yeah. RTC stands for real-time clock.
Yeah. And as you saw, and by the way, if you guys have any questions, something doesn't work, just let me know. Yes. Servo? Red? Where's the red? Oh yeah, servo. Search up servo. S. No. S-E-R.
Here,
There you go.
I'll put the part names here.
Yeah. So, we will explain the code later, but before the code, we will connect the wires correctly first. So as you saw me do it right here, we will make sure that wires are connected properly. Now, if you hover over some of the pins here, like for example here, it shows you what is the ground wire, what is the V plus wire. V plus just means power, and what is that is the PWM, which is simply just a varying voltage like line, right? And that's how that servo actually works. That's how that servo actually works. Is that by a varying voltage, it will rotate according to it. So the higher voltage, it will rotate like 180. A lower voltage, 90, such and such. So we will start to connect some wires. So if you press on the ground on the servo, we will have to ground that to the board. So when you press on it,
You can drag it over to ground.
I don't think you pressed on it.
I did. Oh, max.
No.
Ah,
Just press it.
okay.
There you go. You connect it to just one of the grounds. We'll connect it to ground 3. Okay? And we will then connect the power line and make sure the power line is connected well.
The red one.
Oh, it's right here. Instead of 5V.
So this one will go to the 5 volt, which will be the power to the servo.
Yes. And then we will connect the PWM, which is the pin that we will manipulate in the code, to pin 9. And that's important because while you were in the code, you want to make sure that you will see later on, you want to see that you are writing code for pin 9 and, for example, not pin 8, because pin 8 has nothing to it, so nothing will happen. So stuff like that. And we have to do the same with the potentiometer.
So this is the ground.
So we connect the ground as well. As I said, there's a ground for each component. Yes? PWM goes to pin 9. Up there. Right. Up there. Yeah, there you go. Okay. Potentiometer, so you connect the ground first. What ground did you connect it to?
Which one?
So you look over here. Yep, it's just ground 1. Yeah. And the fun part is not here yet, guys. Gotta start coding. Then we keep connecting the wires. So you go to the VCC, which is kind of like the V+, it's just power. You connect that to
also power, right?
also the 5 volt. Yeah. And signal as a SIG port, and
That one's staying 0, I believe.
that just it goes to this pin, and it's a little bit more technical, but we don't need to explain it. You'll see how it works in. And we just have one component left to work with, and that's the real-time clock. So it has a couple more pins. So first, the easier parts are the ground first. Make sure the ground is connected, and we'll connect it to the second ground pin over there. It doesn't matter. And then we'll connect the ground. The power. 5 volt. Sometimes the reason why there's 2 power lines is that there's 3.3 power pins. Sorry, there's 3.3 volts and 5 volts. Some components are built by an electrical team to require only 3.3 volts, while others require 5, and that's why there's kind of 2 power pins over there. And now you can tell that there's an SDA line and SCL line, which is what we were working on over here. As I said, these are for the communication protocol, I2C, and we will just have to connect them to the right pins. So we'll connect them to, it even highlights what are the right pins for it. And that last pin, some pins are unnecessary. You don't have to connect all the pins, like on the RTC board. Now we're done connecting all the components, hopefully connected them right, and now we're going to start writing some code. Now there's one thing to say. This is Arduino code, and this is a structure. It's basically a simplified structure that simplifies your like intro to embedding. So there's two functions. There's a setup and a loop. Setup works once. Setup runs once at the beginning of your program. It's the first thing that runs. Setup runs once. Loop constantly loops. So you'd understand, you'll realize that sometimes you have sometimes you have some code that you only want to run once and not ever again. Things like initializing a variable to 0. You don't want to initialize it to 0 every time. That may reset some counter. You just want to initialize it once, and then that variable can then be used in the loop function. So let's start. So you don't have it in the library manager? It's not there automatically?
I mean, no, because this is a blank project.
Okay, sure.
Yeah. But
I think you do it through the library manager better, because I'm not sure if just writing it like that works.
what do you mean?
There you go. So with components, sometimes they have libraries. Libraries is basically like an API, if you ever heard of API. And APIs makes your work easier. So these components, they all have registers inside where they're manipulating some value. But let's say I want to turn an LED on. If I didn't have the library, what I would have to do is change the value in a register, which is very low level and very hard to read. But API, API and libraries, what it makes it do is just, it has a function already written where it just says, turn on LED. And that's the importance of libraries.
So because we're working with the servo and the RTC, we're going to use the libraries for each of those components.
Is it in library manager?
It should be. That's how I do it.
Yes. See, I don't think it's actually. So we will try. We will have to add them through here.
Because it gives you the ones for each.
I know. Yeah.
Yeah.
So the servo one is a little bit harder to find. You'll have to scroll down until you find a
Just
servo.
Okay.
And
See.
well, RTC lib added on its own. I think it's because we wrote these 2 lines of code.
Yeah. It should import them automatically. It might just take a second.
Yeah. You guys have that done? So the include, this is something that is only specific to C, and include is simply just to, it's what it says. It includes a library. So we choose what library to include, like servo, like RTC lib. Once you get into whatever programming course you do, or if you already know, there's a reason why it's .h, and you know, .h and .c has a certain significance in C programming. Okay, now we will want to do something. We want to initialize some values that we can help us use them while writing the code. We will also want to rename some things. So the name of the RTC component is quite long. It's RTC DS1307. And we just want to simply change the name into just RTC1. Just so, and this is the thing about readability. Readability isn't only for luxury. Readability is quite important in embedded programming. It makes some certain other user who's going to look at your code later know what they're looking at. So you want to make your code readable. And now we're going to initialize some variables just so we can use them later. So we're going to initialize a variable called pin. And in C, if you've ever done C, this is how you initialize variables. Int is kind of the type of the variable. So that just means that pin is always going to be an integer. Whenever we use pin, it has to be an integer. That's what int is. We're also going to have int val, and you'll see why later. And then we'll continue writing some. You know what? We'll add that while we're coding, because I don't want to explain that right
Totally
now.
confused.
Okay.
So,
Now, we will start coding in the setup function. So we want things to run once. In I squared C, you have to begin your serial line. And basically what that means is you have to kind of set the, basically this opens the serial ports on your boards, and it just basically lets the program know that, oh, there's gonna be some communication in between boards. The 11,000, that number is just simply the speed. Why that's important is because sometimes you want to have several serial lines on the same boards, such that like they have independent serial lines. So how that would look in code is it would be like serial.begin that number, and then serial1.begin another number, just so you know that they don't interfere. But we're not gonna do that right now. And now we have to write in code that servo.1, servo1 is attached to pin 9. And that's actually what we did through the wires.
you can see the green wire here
Yeah.
is running to it.
And make sure you write the semicolon. So in C code, after every line, you have to write a semicolon, or else you have compiling errors.
That
And
one
now,
skip.
yeah, we can skip that. So there's in embedded programming, there's also error handling that must be taken care of. You must be able to error handle in your code. So we're gonna have something right here. It's just a check statement that checks if the RTC component is turned on or not. The clock, if it's turned on or not. So what this line does, let's just look inside the bracket. RTC1.begin, it turns on the clock component, which is the RTC, the blue one. The exclamation mark you see is actually, we call that a not operator. So what this does is checking that if RTC is not already begun, right, we're gonna print some debugging handling code right here where it just says, it tells you, oh, we couldn't find RTC. That's because Arduino, one good thing about Arduino is that there is a terminal that you can print stuff to, which will help you in debugging. Kind of like if you've ever coded, you want to see like what value is at some iteration, you do console.log. Now, abort is simply to abort is simply just to shut down the program if this is not working. It's just so the program doesn't keep running.
In other cases, if you were to have very vital components hooked up that depend on the RTC to not break, you would want it to abort if it can't find the RTC. So,
yeah. And then we're gonna have another error handling function that checks if RTC is running or not. This is also important just in case, you know, it boils down if we ever have issues to know what the issues are. Imagine this, if we didn't have these error handling if statements, then if something goes wrong, the program will just crash. What crashed the program? I have no idea. The reason why we do this is so that if it programs to this reason, oh, I know that's the reason why it's not programmed. It's just, we create our own feedback, simply. We create our own feedback system. So here we'll have a line that it simply adjusts, because what you would have is that some of these RTC boards, their issue is that from the manufacturer, they're set to the date and time that the manufacturer made them at. So you kind of need to update them if you ever want to use them. And that's why on this code, we want to make sure that it's adjusted as soon as we run the code. I think that's like intrinsic, right?
yeah. These are variables that are built into this IDE. So we're just going to use those.
Yeah. Date, T, and time, it's basically
Oh, whoops.
built in to already have, date, to already have the current date and time, just to use them whenever you want. So what we're telling the RTC to do is just to adjust to this time, which is now. Now, what we would like to show is that we want this, what we want to happen is we want to know the angle of the servo every second. To do that, we have to have some sort of something that tracks down the angle of the servo and then prints it every second. But every second, when we say every second as programmers, it's not so easy. Every second actually requires you to set some variables. So we're going to go back into the setup function, above the setup function, and create some variables. So we're going to call them, call it start time. So unsigned long are just other data types. It's a little bit more technical to the C programming languages, but it's simply because it's just to make sure that it always stays positive. These numbers are always going to be positive. Unsigned means it's something to do with like bit knowledge, how you understand binary. It's just so that it doesn't have a bit that tells it if it's negative or positive. Unsigned means that the entire binary number is always positive. It's a little bit more technical, but you can just follow along. And identifier, yeah. It's simply just, we set a constant. If you try to change this variable later to another number, it wouldn't work. It's good for readability. It's also to save memory on your board, which is quite vital when you're working with very vulnerable systems like this. You want to minimize the amount of memory you use all the time.
Since we want to get an update from the servo every second, this 1000 is in milliseconds. So that's why we're setting it to this as a constant.
Yes. Now we're going to go and we're going to go in the setup and make sure that start time is set to, is just some start time, whatever it is. It's just a timer that starts at 0. Whenever this code runs, this timer is just starting at 0 and then it starts counting up milliseconds. Millis is just a function. It's simply a counter of time. You can read into the function later, but some things you just know and you know how to use them. You don't need to know how they work yeah.
On that note, Walkwe actually has extensive documentation about all of the functions and all of the different components. So if you ever want to play around with Walkwe, they have all the info you need in their documentation.
Yeah. So, okay. Yeah. So, we're gonna also, how we use the current time is that we always want to check the difference between current time and start time, simply because the loop is constantly looping. So we want to wait until it finally reaches 1 second. We'll more on that later. And now we want to use the potentiometer to basically read the position of the potentiometer. Here's the thing with embedded. You can't just code simply on what you see. In embedded programming, there's a huge focus on reading documentation and making sure what you're reading. So usually in embedded programming, what you do is that you constantly have to look at the board, and that's what we did. As I said, I knew that the 1.6 line is the SCA line and 1.7 is the SCL on the MSP board, but I had to go through documentation and find out which pin it is, because there's a lot of pins, I don't know what any of them do. So you got to look at the data sheets and learn. Same thing with the Arduino. So anyway, right here, we don't know how to read the, the whatever the value of the potentiometer is. So here's what we do. And Wakwi actually, this website, it does a good job at simulating also how an embedded engineer would have to constantly look at documentation. So we would have to go to, open a new tab and search up Wakwi documentation. And you enter this website, and here it has documentation about all its components. And on the search bar on the top right, we're going to search up potentiometer. It should be that one, yeah. No, it was the first one.
Well, there are two different kinds. This is the knob one.
Yeah. Yeah, slide potentiometer, slide on the first one. There you go. So there you go. Now we need to make sure that we find the right component. You don't want to read the data sheet of another component when you're dealing with one component.
I believe you can also click on any component and there's a little question mark that pops up. And if you click on that, it should take you to the page.
Good. So there should be, if you scroll down, use of functions. No, okay. That's all right. We will go back to this later. But if you go back to the code, we will now set the value, the variable that we created before to read the value of, so pin is the pin 9 that we set to before. Analog read is a function that just gets the value of whatever that pin is set at. So understand that when you're sliding this potentiometer left and right, that value changes. So you have to constantly, in a loop, keep updating the value to constantly read what is at that pin. Next, here's the thing. So here's the thing where you need to learn about documentation. So this servo can only rotate between angles 0 to 180 degrees. But this potentiometer, if you go back to the potentiometer, you'd see that the minimum value is 0, but the maximum value is 1023, which is way higher than 180. So you have to do this thing where you do a mapping, is what we call. So you have to map 0 to 1023 to 0 and 180 so that the servo reads the numbers correctly. If you do not do that, then 180 will simply be like the first sliver of when you move the potentiometer, then the servo will already be at 180. So you kind of have to map it. And there's a function that we use is called, it makes it easier with the libraries that we're getting here. We're gonna set val, and we're gonna map the value of val, which is from 0 to 1023. We're gonna map it to 0 to 180. Sorry, 180 to 0, yeah. And that's just simply because why we change like which one comes first is just simply so that when you slide it left to right, it rotates clockwise rather than anti-clockwise. It doesn't matter. It's just a small little detail. And then we're gonna write that value onto the servo. So the servo can then get updated with that value, which is what we're doing with .write val over here. So servo 1, remember, is a servo that we're using. And when we write .write to it, it simply updates the degree of the servo. And we're also gonna have a variable called now of type date time, and we're just gonna get the current time of the RTC, which is, if you go into the RTC documentation, there's a .now function, and which gives us the current time of the RTC. How we knew that is we had to go to documentation and learn that there's a function even called now. Now, we want to have an if function that finally checks if the difference between current time and start time is greater than the period. What that is doing is that, so if you can imagine, current time is constantly updating, okay? When it finally reaches above 1 second, we want it to execute whatever we want it to execute. If it's not greater than 1 second, then don't execute anything yet, just keep looping. Okay? So this is important so that we can write to the console only every second, never any other time. And now it's basically quite easy. So I actually think you can run the code, right?
Yeah, I should be able to.
Over here. And the potentiometer should work. Yeah, just cancel it and run it again. So yeah, Wakui kind of has a problem where like you have to compile several times for it to ever compile, or else it just waits there. Keep pressing on it. Maybe save it first. That's what I did last time. It worked. Save it at whatever name. And then run it.
That's not great.
Come on, hopefully it
I'm gonna
works.
try it here too. This one's working.
This one's working, but this one isn't.
Okay. I also have the actual thing saved
always
in the
does
other
that.
window. Oh, okay.
Run it again.
Okay. I'm gonna see if this one works. Yeah,
All
this
right,
one's
this
fine.
one works. So this,
Just
as you can
ignore
see,
that the bottom part. We haven't put that in yet.
we haven't done that yet.
But you
Yeah.
can see that the servo moves exactly when we move the potentiometer, which is the
Yeah.
main goal of this project.
Which we successfully did in that bit of code up there.
Yeah.
Scroll up. Yeah.
Just in this code right here, that
Yeah.
is what is accomplishing this because of all of the hookup that we did and the variable naming and all of that.
Yeah. And just for it to be useful, we're also gonna try to write that little thing, the thing to make it update every second, so we can see, the value of the degree. So we'll continue writing. Is it because of this? Maybe it's like going in there and not doing anything, even though it shouldn't.
I don't think so.
Okay, never
It would
mind.
just exit.
All right. So now we're gonna create a string. A string is just a lot of characters. Yes. Probably just needs a refresh.
Yeah.
Yeah. So it does that sometimes. This thing is finicky. The simulator. Sometimes I've had to deal with it where I just have to ask it to run several times for it to ever run. Where does it say build failed?
It opened a
When you
little
do what?
pop-up. I refreshed it and it opened.
Okay.
So I think it tried to build automatically.
Yeah, it tried to build on its own, but it just doesn't build for some reason. So string is another data type, just like int, but it just holds characters. Characters are like A, B, C, D. So we're first gonna set it to nothing, and then in code you can concatenate strings. So we want to set, we're gonna set this time variable to have, we're gonna make it nice. What you can do is you just write, you add to the string the value, the current values of year and month and second, but it wouldn't look good. It would be basically unreadable. It would just be numbers next to each other. The reason why we're adding brackets and slashes like that is just to make it readable in the.
You can see that the way the time is formatted here, we're doing that manually right over here.
Exactly. So this part is quite easy.
It's just tedious.
Yeah. So you have a space for the now.year. Now.year is now is just an entire, it's like an entire list of numbers. When we do now.year, that is directly from the library of RTC, which it will help us only to get the year, only to get the month, only get the day. You can understand now, without this library, how annoying this would be. There wouldn't be a now function. There wouldn't be a year function. You would have to annoy yourself with going to the register of the component and getting the value from the register. And you have to find out which register. There's many registers on the board. So that's why these APIs just make it far more easier. Now we're almost done with the code. We only have like 5 lines left and the entire code, and we'll be done. Are any of you having an issue here? No? Yes? Sorry? Oh yeah, it's okay. I can do it for you. So ground's up there, and this VCC connects to the 5-volt down here. Yes. This just goes to this pin. This connects to remember this ground. This
one to one.
no, sometimes you can connect more to one, like for example this one. So we'll set that here, and it tells you where to go. And hopefully the other pins are connected correctly, but for now it's good, and I'll let you know. If it doesn't work, then it's probably that. Yeah, welcome to embedded programming, guys. Okay, and so now we're gonna, we have this time string now that we successfully set up to have, you know, the data, the time information in it, and now we're gonna print that string to the serial log. Okay, and we also want to print the angle, so we're gonna print just, you know, the word angle in like a string. So here's the thing, you put quotation marks when you want to like just write words, like whatever words, and you leave out quotation marks when you just want to print a variable, like time. If you put quotation marks around time, it would just literally print out time, like that string. So, and then we write, yeah, minus val plus 9. So the reason why we did it like that is just because if we just printed out val, it would be a variable between 0 and 180. Having, now that we minus 90 to it, it makes it easier just to see that it's from between negative 90 to 90 degrees. Just like that, right here.
Sorry,
You know, run it.
it's not running.
Yeah. So it's just instead of seeing 0 to 180. You could have kept it, but it's just ease of readability. And then we write serial.print degrees. And we're 1 line left. We're almost there. There should be something important to note. There's 2 different prints. There's print and print ln. Print ln simply goes to the next line and writes whatever you want it to write. Print on the same line. So sometimes you want to go next line, but sometimes you want to stay in the same line. For example, imagine if we did print ln to all those prints, what we get then is in time, and then the next line is angle, next line degrees. We want to keep it on the same line. So this last bit of code is very important. You want to reset the start time to be to the current time, And because if you didn't do that, then understand that above there, we're in the if statement, we're checking the difference between current time and start time. When we set start time to be current time, that means when current time gets updated, it gets subtracted from only the previous second. If we didn't do that, then it's gonna be always above 1 second, simply. That's basically the structure of like code to make sure that stuff kind of works. Now it should work.
It should.
If you simulate it and run it.
I'm gonna save it and refresh.
Does it build now? Ugh. Does it build for you guys?
It might be a library issue.
I think so.
That's usually the case.
Do you have a library?
Oh, it's working.
There you go. It's
It just
working.
took a long
See,
time.
it's annoying sometimes.
So we can't see the server.
So there you go.
So 1 second.
Now you've coded your first ever simulated embedded programming function. Yeah, so this is a little taste of what we do. Now we do this with real parts. This is the intro task if you want to join the software team. You could save it and upload that, or you could redo it again on your own. But this is essentially a simulator of what we do in real life. It's just a lot of documentation reading all the functions, what functions can be used. Hey, I want to use this function. Is there a function already in place, or do I have to make my own? The fact that now, imagine this physically. Now that you're moving this potentiometer, it's moving something else entirely, just by programming, right? So how would this not work? For example, here's a couple of mistakes that we can that happens to us. You see the servo.1 attach, servo1.attach. Attach it to rather 8. Change it to 8. Here's a mistake you could have done. When you simulate this,
If it runs.
I hate it. I hate it so much. Save maybe?
Just so you guys know, there's actually also a research part to the intro task. So you would do this part as a practical, and then for the research part, you would have to answer a couple of questions about how some of the communication protocols work. So it gets you kind of more familiar with like I2C and things like that.
Okay, now let's change the potentiometer, move it around. As you can see, because we connected the wrong pin, what has happened now is that the servo is reading value from a wrong pin, from an entirely different pin. So what you think should happen, which is I'm moving potentiometer, the servo should then turn around, is actually not happening. Understand that the reason why the angle is changing is because the angle is entirely separate from the servo. The servo, the only thing it's doing is that it's just relaying the information from the potentiometer to be moved around. The angle that we're receiving in the in the log right here is from just actually us having a completely independent variable that's just reading from the pin itself. So it's two independent things. And that's why you would be confused and you wouldn't understand why sometimes stuff doesn't work. Try one thing. Remove that last line. Go down. Where we don't reset the start time to the current time. When you run this, it will simply print, I'm pretty sure, every millisecond. And you don't want that. You know, it also could be internet issue. There isn't the best internet here.
Yeah.
There you go, you see that? So the reason why it's doing that is because we're going above 1 second once, and now, because we're not resetting the start time, we're always above 1 second. So it's always printing, okay? So that's why that last line was very important. So I'm showing you this now from a perspective of somebody that has now figured it out working, and I'm now making the mistakes. Imagine how you would actually work about this when you're programming, is that you would make the mistakes first and be like, wait, what's the fix? Wait, what do I need to do? So you try other things. And then, like, why this is important is because sometimes you would need to debug. And by debugging, you would realize, like going line by line, you would realize that, oh, start time is always 0. So when current time is counting, the difference between current time and start time is always above 1 second. So, yeah. That was it for the intro to embedded programming. Hopefully you guys did your first embedded programming function. Did it work for you guys? No? Did it work for anyone here? No. Damn. Wow, what's up? Okay, I see a mistake here. So there's no bracket. Yeah, so you need to add it, or else you're using functions from somewhere that doesn't exist.
Okay, everyone, while Amro goes around and corrects our brave participants who tried out our workshop today, I'm just going to close us out for those of you who are online. So thank you again to ADH lead Amro and ADH member Rowan for this wonderful intro to embedded programming workshop. Space Day continues here at 4Space at 3 p.m. We have a parabolic flight video and a short discussion coming up for you guys. So thank you to everybody involved in the workshop for coming into 4Space today and activating this. And for those of you online and here in the space, thank you for your questions and contributions as well. We're going to be closing up the live stream now, and a quick reminder that this workshop will already be available on our YouTube channel at the end of this day, so you can always revisit or share. So join us again. Like I said, at 3 p.m. we'll be doing a parabolic flight. Thank you.